Good evening and welcome back from break. Welcome back to your AP Stats Notes Online with Mr. Smith's AP Stats class. Want to continue talking about scatter plots. And so when we left before break, we were discussing explanatory response variables, trying to find a relationship between two quantitative variables and trying to determine if there at least appears to be a relationship between two quantitative variables. I say appears to be because we know that in order to establish a cause and effect type of relationship, in order for an explanatory to definitely cause a change in a response, we'd need to set up an experiment, a well-designed experiment with treatment, control groups, the whole nine, to establish that sort of causation. But we're trying to at least see if there appears to be a relationship worth talking about. And so we do this in the same manner that we've done everything else, right? We collect our data, we find some way to display that data, and a scatter plot is how we choose to display it. What we want to do now is try to find a way to model it. Density curves model single variable or what's called univariate data when we only have one variable that we want to take a look at. How do we model two variable data? How do we model plotting two quantitative variables next to each other? And the answer to that question is with a regression model. Okay? A regression model can come in two forms. It can come in the form of a line or a curve. We'll, for right now, focus on lines. And a regression line, by definition, is a line that we use to predict how a response variable, or a y, will change as an explanatory variable changes. Okay? Another way to say it, and I think if you read in your book, the definition is a regression line is the line that we use to explain how a response variable changes as an explanatory variable changes. It is a way to make predictions, right? Least squares regression, sorry, not least squares. We'll talk about least squares in a minute, but a regression line is a line. It's so linear equations, and so you can get an equation of a regression line the same way you do for any line that we talked about in Algebra 1. And the equation of that would look something like this. Y hat equals A plus BX. Okay? In statistics, that's typically the form that it takes. Right? And so there are some things here that we need to understand. First of all, Y hat is a predicted response value. Okay? It's what our model would predict a response value would be given any explanatory value. So any x, we're trying to predict what would happen to y. So y hat is our predicted response, and it's a major deal that we know the difference between y hat and y, and we're going to talk about that in just a second. A is our y-intercept. Okay, if you're looking at the y equals mx plus b model, it's a little confusing, but A typically is what we'll reserve as our y-intercept, and B is the guy next to the x, and so B then obviously becomes the slope. Okay? We'll talk about how to interpret the y-intercept and the slope because we want to interpret everything in just a minute. But that's the form of a regression line. Y hat equals A plus BX. Now, you always want to sort of add in context here. And so we would want to fill in y and x in the actual terms of a problem. And I'll show you what I mean in just a few minutes. But that's the form it's going to take. And it should look familiar and not too crazy for you. Y again is our A is our y-intercept and B is our slope. Now, I want to skip the least squares regression line for just a little bit. I don't want to worry about that right now, so I want to move my box around. I had the box up here because I don't want you focusing on writing instead of listening. Great. As this stuff slows down, it makes this a little tougher. That's okay. We'll figure it out. So if I move this down, this is not going to work. All right, let me change boards here. Maybe that'll go a little bit better. Okay, I'll come back to the least squares regression line in just a little bit, maybe tomorrow night in our notes. We'll see what we get to tonight. But so I mentioned that there's a huge difference between y hat and y. And again, context being king here. We'll add context a little bit later on. But for now, what is the difference between y and y hat? Y is the actual response value from your data. So whatever we've chosen as our response, we're going to measure that response, and that's going to be our actual y, and we're going to denote it by an actual y. Anytime you put a hat above anything in statistics, then we're talking about the predicted value. So y hat is always your predicted, and it's whatever from our quiz, age and systolic blood pressure, which we'll get back tomorrow. Systolic blood pressure is the response variable. So we're going to actually measure someone's blood pressure, and that would be an actual y. Y hat would be if we used a regression line in the equation for that regression line. If we use this equation to predict what it would be for a certain age, then that would be our y hat. That's our predicted value. Okay. You've got to be really careful about mixing and matching those two symbols. You have to make sure that you remember that y hat is for your predicted and y is for the actual. There are a lot of points lost on the AP exam for not remembering that difference. Okay? But there's the difference between y and y hat. Next up, how do you interpret the slope and the y-intercept? Let's keep talking about our equation here. Slope. Now, I don't know that we talk about it very often here at Franklin Central, but slope is really the change in y over the change in x. How does y change as x changes? And we'll take this one step further, and when we interpret slope, what we do is we talk about as x increases by a unit, and we need context in all of this, but basically as x increases by 1 unit, y increases or decreases by this much, right? In other words, we want to talk about as x increases by 1, what's going to happen to y? Is it going to increase, decrease, and by how much? And again, all this stuff needs context. Our x will need context. Our unit here will need context. Sometimes it's not 1, it's 100 or 1,000 or whatever. But as we increase our x by 1, what's going to happen to our y? And so our y will need some context. We'll need to choose increase or decrease, and the sign on our slope will help us do that. And then we'll need to add context by how much the y increases or decreases by. And this is very vague and general and maybe a little bit confusing now, but we've got an example here in a second that we'll do that with. Okay? The y-intercept is like it always was. The y-intercept, right, if I were to graph an x and a y here and then put some line in here. So our slope is, as we move from one unit down the x-axis, then it's supposed to tell us, let's see, here to here, how our y moves. Okay? Now, the y-intercept is always where the line touches the y-axis, which means that our x has a value of 0. So when x is 0, what's y going to be? And sometimes that y-intercept doesn't make a lot of sense it just becomes sort of a value holder in the equation. And so we still need to interpret the y-intercept. We still need to know what it is and what it means. But very often it's a nonsensical value. And it deals with the fact that in our scatter plots aren't always starting at the x and y axis. It's not always starting at 0, 0 and then showing us it's again, as we scale our y and x axes, sometimes it doesn't need to start at 0 and to capture our data. So we'll get into some examples where the y-intercept doesn't make a lot of sense. Okay. So let's continue on here and get to our first example. And this is Honda CR-Vs. And so let's imagine you're shopping for a Honda CR-V, a little mini SUV there. And so this scatter plot shows the number of miles driven and the advertised price for 11 used Honda CR-Vs from 2002 to 2006 model years, okay? And so we have our data here. These points are actual cars. You actually went out and found these cars. There's a car that had a little less than 40,000 miles on it and was right around a $14,000 price tag. Okay, so that's an actual car. This line is our regression line, very often called the best fit line. There are some different types of regression lines, and we'll talk about that in just a second. So this line has the equation y hat equals 18,773 minus 86.18x. Now, there are ways of getting that equation. What we're going to talk a lot about is how to use our calculator to do it. It'll do all the heavy lifting for us, and we're not going to have to worry about finding slope and y-intercept. Okay? Our calculator will do all of that for us. But we've got the equation already. We'll worry about getting that later. Right now, let's just talk about what the equation means, right? And so what I mean by plugging in context to the equation from earlier, we could write the equation as y hat equals 18,773 minus 86.18x. Or to satisfy context, very often what you'll see is since cost is on our y-axis, we could actually put that in here. We could go cost hat equals 18,773 minus 86.18. And instead of writing x, since our x is thousands of miles driven, we can include that here and just go miles driven. I'm writing over here, and I apologize, but so that would add context for us, and probably not a bad way to write out your regression equations, because it helps in the interpretation and helps remind us of our context. So let's interpret the slope and y-intercept. Well, first you have to remember that this guy right here is your slope, right? And this guy right here is your y-intercept. Okay, so what do those two things mean? Well, first off, your slope is negative 86.18. Now, in Algebra 1 class and Algebra 2 class, we very often liked our slope to be in the form of a fraction, right? Because then we can get our rise and run out of it. Our change in y over the change in x. How much does x have to change, which is your denominator, in order to get a certain change in y, which was your numerator? In statistics, we don't need that. We're going to go ahead and divide out our slope and get a decimal, because we don't really look at it in terms of rise over run. What we look at it as is in terms of we're going to automatically assume that the x increase is going to be by 1 unit every time, right? So with our slope being negative 86.18, and we need some context, let's interpret that slope. We interpret that slope as simply this. For each 1,000 miles driven, so as I go from, as I walk across the x-axis by 1 unit, and our units are 1,000 miles driven. So for each 1,000 miles driven on a Honda CR-V, the price is predicted, remember the equation's always predictions, the price is predicted, so that's pretty important to include, to decrease. Why decrease? Because our slope here is negative. So the price is predicted to decrease by $86.18. Okay? So for every 1,000 miles, I should expect a Honda CR-V to drop in price by $86.18. That's what I would expect, or that's what I would predict. Now, a great question would be, okay, where does that price start? Well, the price would start at when our miles driven was 0. And that's 0 on the x-axis, and so that would be our y-intercept. And so our y-intercept, being 18,773, simply says that for a Honda CR-V driven 0 miles, or in other words, being brand new, the predicted price would be 18,773. Okay? Now, I don't know from 2002 to 2006 if that makes a lot of sense or not. If Honda CR-Vs were that inexpensive, I don't know, inexpensive, 18,000 might sound like a lot. But at least from this regression model, then that line is a model, just like a curve, a normal curve is, modeling of single variable distribution. That line is just a model. Our model suggests that with a brand new CR-V would cost about $18,773. Okay? That's how you would interpret the slope and the y-intercept. For a 1 unit increase in x, right, and this was our x, this is what we would predict our y to do. Either decrease or increase, decrease here because it's negative, and then $86.18 is our context. Our y-intercept, for x to be 0, so for 0 miles, this is what we'd expect the price to be, $18,773. Okay? That's how you would interpret those slopes. Okay? And then the last question here, what is extrapolation? And why is it dangerous? Okay? Extrapolation simply means this. It means that if we're going to extrapolate, it means that we're using values far outside the interval of values for x, for our explanatory, to make predictions for the response. Why is it dangerous? Because we're using numbers, we're using data outside of our window of our scatter plot to make predictions, and very often it's not very accurate. So in other words, extrapolating would be trying to find the price of a Honda CR-V that's been driven 150,000 miles. 150,000 miles is way outside of our data window here. So we don't know what happens here. We don't know that the dots continue to go down in this linear pattern, or it's possible that these dots sort of flatten out, right, like this, or something really crazy happens, and for some reason the price increases as the miles driven increases. Now, it doesn't make a lot of sense, and it probably doesn't do that, but it would have to, at the very least, flatten out, right? I mean, for 150,000 miles, if this line continued to go down, then we're looking at a negative cost, right? So what does that mean? I mean, if I find a Honda CR-V that has been driven 150,000 miles, that someone's going to pay me to take their car? I don't think so, right? So extrapolation means using X values way outside of our data window to try to make predictions for our response. And very often, those predictions are not very accurate. Okay? All right. And so we can stop there with our definitions. I want to make sure that we're picking up everything that we need to do here. So in your book, and hopefully you brought your book with you, But if you didn't, I'll put this up here for you to take a look at. There's a check your understanding on page 167. And it's talking about rats, male white lab rats. Take a look at that check your understanding. It gives you an opportunity to take a swing at interpreting in context the slope and y-intercept for a regression line, and a couple of extending questions there. So take a shot at it, see what you come up with. We'll start class off with that check your understanding, and then use the rest of the time for you to work on the homework. Homework is in the text that should be out, and we'll see you guys tomorrow, and enjoy your evening.